Welcome back to Let's Talk About Data, Season 2 of our Data Science Project series. In today's episode, we're diving deep into speech-emotion recognition, teaching machines how to detect human emotions from voice recordings. This is Episode 2 in our 10-part series where we implement real-world, production-level data projects end-to-end. Why does speech-emotion recognition matter? Imagine a world where customer support bots aren't just reactive, they're empathetic. By enabling machines to detect human emotions from voice recordings, we move beyond rigid scripts to intelligent systems that sense frustration, joy, or confusion. These bots can dynamically adjust tone, response strategies, and escalation paths to enhance customer satisfaction. Now think about mental health monitoring. Traditionally, emotional well-being has been hard to track continuously. But SARE opens the door to non-invasive, passive monitoring tools that can detect early signs of emotional distress, potentially transforming preventive care and reducing mental health crises. Next, consider personalized education. Imagine an e-learning app that senses when a student is disengaged or confused, and then adapts its teaching style in real time. Similar to product recommendation engines, this form of intelligent tutoring creates a learning journey that evolves with the student, not despite them. This isn't just about algorithms, it's about building production-level, human-centric solutions. Now let's dive into the key components that power this exciting speech-emotion recognition system. At the heart of our model is a powerful resource, a labeled dataset of emotional speech. Each audio clip comes with a predefined emotion tag, making it ideal for supervised learning. These datasets are critical because they provide the experience a machine needs to learn from, mapping raw audio features to specific emotional states. This foundational training enables the model to generalize and perform accurately on unseen data.
Kids are talking by the door.
Let's now look at the tools driving this system forward. Python, the core of modern machine learning. Python's clean syntax and powerful ecosystem make it ideal for quickly building, testing, and deploying ideas. It allows us to move fast from prototype to production, keeping our project agile and scalable. 2. Librosa. This specialized audio processing library enables us to extract meaningful features, like pitch, MFCCs, and spectrograms, from raw sound. Without Librosa, we'd be stuck with high-dimensional data that's difficult for models to understand. 3. Scikit-learn. A cornerstone for traditional machine learning. Scikit-learn offers everything from classification algorithms to evaluation metrics. It helps us train, validate, and optimize models with ease, ensuring they deliver real-world performance. 4. Streamlit. Once the model is ready, it needs to be showcased, and that's where Streamlit shines. This tool helps us build interactive web apps straight from Python code, making it perfect for creating a real-time demo where users can test the model hands-on. Together, these tools enable us to build a full-stack machine learning pipeline, from raw data to an interactive web interface. It's not just about model accuracy, it's about creating systems that work in the real world and are accessible, maintainable, and impactful. Let's dive into the foundational first step of our speech, emotion recognition project, pre-processing audio. The first step is to load our dataset, an extensive emotion-labeled collection of speech samples. But here's the challenge. Machines don't understand raw audio like we do. A microphone captures tens of thousands of samples per second, each just a measurement of sound wave amplitude. This raw waveform is incredibly high-dimensional and chaotic, making it difficult for any model to extract meaningful emotional patterns directly. It's similar to how a raw image is just millions of pixels. What matters isn't the pixel values themselves, but the abstract features that describe what's actually in the image. This leads us to a core principle in artificial intelligence. It's not always obvious what features should be extracted from raw, high-dimensional data. While deep learning can learn features end-to-end, in audio applications it's often more efficient to transform the input into a format that better reflects how humans perceive sound. This is where mel-frequency cepstral coefficients, or MFCCs, come in. MFCCs are specialized features designed to mimic how humans perceive sound. Just like our ears don't process raw waveforms, but instead respond to frequency, tone, and rhythm, MFCCs extract those perceptual features. Here's how it works. First, the raw audio signal undergoes a Fourier transform, converting it from the time domain to the frequency domain. This creates a spectrogram, a visual representation of sound over time. Then, using a scale that aligns with human auditory perception, the MEL scale, we extract coefficients that capture the essence of the sound. MFCCs are especially powerful because they make the model equivariant to frequency shifts. That means if the same melody is played in a different octave, it still produces a similar feature representation. This aligns machine perception with human perception, which is key when detecting nuanced emotional cues in speech. To implement this, we'll use Python and the Librosa library. With just a few lines of code, specifically using librosa.feature.mfcc, we can convert every audio file into its corresponding MFCC features. This makes the data not only digestible, but deeply informative for our machine learning model. This stage of data preparation is absolutely crucial. It's more than just converting data, it's about crafting a representation that helps the machine understand the problem space more effectively. The decisions made here have a massive impact on model performance, especially in real-world production-level applications like ours. With our structured MFCC features extracted, we're now ready to move on to the next phase, building and training our emotion detection model. Now that we've transformed our raw audio into meaningful MFCC features, it's time for the heart of the project, building our emotion classifier. We're tackling a classic multi-class classification problem, where the goal is to train a model that can recognize and categorize speech into 4 distinct emotional states: happy, sad, angry, and calm. But before the model can learn, we must first structure our data correctly. Step 1. Split the data. The first critical step is splitting the dataset into 2 parts, a training set and a test set. The training set is where the model learns the mapping between audio features and emotional labels. The test set is held back, never seen during training, and is used to evaluate the model's ability to generalize to new, unseen data. We'll use a typical 80-20 split, meaning 80% of the data is for training and 20% is for testing. Step 2. Choose the right models. We'll compare 2 powerful machine learning models to see which performs better for emotion recognition. Random Forest, an ensemble model that creates multiple decision trees and aggregates their predictions, known for its robustness even when the data is noisy or complex. 2. Support Vector Machine SVM, a model that tries to find the optimal boundary between emotion classes, particularly effective when used with kernel tricks to handle nonlinear data. Step 3. Tune and validate with cross-validation. To ensure we're not overfitting and to optimize performance, we'll implement K-fold cross-validation, a robust model evaluation technique. The training set is split into K parts, for example, 10. The model is trained on K1 folds and validated on the remaining fold. This process is repeated K times and the performance is averaged. We'll also use grid search to identify the best hyperparameters. Step 4. Evaluate the model. Once trained, we'll evaluate the model on 2 essential metrics. Accuracy tells us the proportion of correctly predicted emotions. Great for a quick snapshot, but it doesn't always capture the full picture. Confusion matrix, a deeper look at what the model got right, and more importantly, what it got wrong. It shows how well the model distinguishes between similar emotions and reveals confusion patterns. This workflow, from data splitting, model training, and hyperparameter tuning to performance evaluation, builds a complete foundation for a real-world production-ready speech-emotion recognition system. Now over to you. Comment your favorite emotion emoji, smiley face emoji, crying face emoji, pouting face emoji, relieved face emoji. Let's see which emotion wins the popularity contest. Now that we've built and evaluated our emotion classifier, it's time to take things up a notch and bring our model to life, in real time. We're diving into the world of live emotion detection through a Streamlit web application that lets you record your voice and get instant emotion predictions. This is the moment where machine learning meets real-world deployment. Up until now, we were working with a static dataset, but in a live application, we're dealing with dynamic, real-time audio, data that streams in as you speak. This shift introduces the concept of online learning, where systems are designed to handle continuously arriving data. While our current model doesn't update itself in real time, it predicts emotions instantly on each new audio input. Here's how it works. As soon as you speak, the audio is recorded and transformed into MFCC features, just like during pre-processing. These features are then fed into our pre-trained Random Forest or SVM model, which immediately returns the predicted emotion. This instant feedback capability is what makes machine learning so powerful. It doesn't just analyze the past, it predicts the present. Deploying our model through a web application does more than just show off its capabilities, it makes it accessible. This is a standard approach in industry, packaging a model inside a user-facing app REST API so it can be easily used, scaled, and improved. We're using Streamlit, a Python framework that's perfect for rapidly building interactive data applications. In a few lines of code, we create a user-friendly interface where anyone can try out our model without touching a line of code. Now, it's worth acknowledging that while our current setup uses traditional MFCC features and classic ML models, state-of-the-art speech systems often go deeper. They use deep learning architectures like ORANs, CNs, or transformers, designed to handle the full complexity of audio sequences. For example, LSTM networks excel at processing temporal data like speech, and WaveNet can generate human-like audio by learning patterns across thousands of time steps. These cutting-edge models are pushing the boundaries of what's possible in real-time audio intelligence. But for now, what we've built is already a significant leap, from a static prototype to a functional, production-ready solution that interacts with users in real time. This is the real value of applied data science, turning abstract models into tools that enhance human experience. So go ahead, try it out yourself. Record your voice and see what emotion the machine thinks you're feeling. Link to the app is in the description. Let us know what emotion it detected for you. In our last segment, we brought our emotion classifier to life with a real-time Streamlit app. Now, it's time to dig deep into how well our models are performing. This is a critical phase where we move beyond building and begin to refine and optimize. It's where data science shifts gears from experimentation to reliability and robustness. Let's start by asking, which emotions are easiest to detect? Where is the model getting confused? To answer that, we analyze our evaluation metrics. While overall accuracy gives us a simple snapshot, for multi-class problems like emotion detection, a confusion matrix is far more powerful. Each row of the matrix shows the actual emotion, and each column shows the predicted emotion. The diagonal, bright and bold, represents correct predictions. Off-diagonal squares highlight where our model made mistakes. By examining these misclassifications, we learn where the model is struggling. Maybe angry is often misclassified as sad, or calm is mistaken for happy. This kind of error analysis gives us strategic insight, not just into what went wrong, but why it went wrong. With this performance baseline in hand, we shift focus to improvement. There are two major levers. 1. Hyperparameter tuning. 2. Advanced model architectures. Hyperparameters are settings that govern how a model learns, such as the number of trees in a random forest, or the C and gamma parameters in an SVM. They're not learned from data, we configure them beforehand. Choosing the right hyperparameters is essential. Get them wrong, and the model might overfit or underperform. We use cross-validation to rigorously test various configurations. Tools like grid search keys or randomized search scale automate this, helping us identify combinations that offer the best generalization. Even small tweaks, like adjusting the learning rate, can dramatically impact results. This tuning process ensures we're squeezing every bit of performance out of our models. Finally, we explore deeper waters, convolutional neural networks. Unlike traditional models, Xians are designed to extract patterns directly from raw input data, like spectrograms of audio signals. These networks shine when working with structured inputs and local dependencies. In audio processing, they learn both low-level features, like pitch or volume changes, and higher-level emotional cues. This hierarchy allows CNNs to outperform classical models in many speech-based tasks. By integrating CNNs, we move closer to modern deep learning workflows, giving our model the capacity to handle complex, nuanced emotional expressions in real-time voice inputs. By analyzing performance with detailed metrics, tuning our hyperparameters with precision, and deploying deep learning techniques like calmness, we're not just building a model, we're building a resilient, production-grade emotion detection system. This marks a pivotal step in our journey, one that bridges experimentation with real-world impact. We've covered a lot of ground. We defined the problem, processed raw audio into structured data, built an emotion detection classifier, and wrapped it all into a sleek, real-time Streamlit app. Then, we rigorously evaluated our model to identify what's working and what isn't. Now, it's time for the final and most exciting step, deployment, the phase where your project moves from your local machine into the hands of real users. Deploying a machine learning model isn't just a technical step, it's a strategic one. It's the difference between an experimental prototype and a production-ready solution. In many real-world scenarios, models are only valuable when they're accessible, usable, and reliable. By deploying your model as a web application, you ensure that anyone, stakeholders, end users, even customers, can interact with it effortlessly. The easiest and most efficient way to deploy your Streamlit app is using Streamlit Cloud. It's built specifically for data science and machine learning applications and integrates directly with GitHub, streamlining the entire workflow. Here's how the process works. 1. Host your code on GitHub. Store all necessary files, your code, models, and dependencies, in a GitHub repository. This ensures version control, collaboration, and repeatability. 2. Connect to Streamlit Cloud. Once your repository is ready, connect it to Streamlit Cloud. Select the repo, specify the main file, typically app.py, and hit deploy. 3. Launch and share. Within minutes, your app is live with a public URL you can share with the world. Users can interact with it from any device without installing anything. Your deployment doesn't stop at launch. In production environments, models must be monitored and maintained. Over time, real-world data can drift, degrading model performance. This is why continuous integration and deployment (C/CD) pipelines are essential. They allow you to automate testing, monitor live performance, retrain with new data, roll out improvements quickly. This is your chance to customize the app's design and user experience. Try new audio features or embeddings. Replace the classifier with a deep learning model like a CNN or transformer. Integrate real-time data streams, APIs, or even voice interfaces. Track performance over time using MLflow or weights and biases. Every tweak you make builds your portfolio, sharpens your understanding, and gives you tangible proof of your skills. This isn't just a project anymore, it's a launchpad for your creativity and innovation. Deploying an ML model is more than a technical task, it's a mindset. It represents the full-circle journey of a data scientist, from raw data through exploration and modeling to delivery and impact. So take this final step. Launch your app, share it, improve it, monitor it, own it. Link in the description.